So good afternoon. So I'm Xiao. I work on the Spark in DBS. The DB, same team. Both of us work for the Spark have worked for Spark over 10 years. Today we'll show what is new in Spark 4.2. I take the first half, and the DB will take the second. So the focus of the Spark is native analytics for data and AI. Spark is moving more of the stack into the engine. Let's start. So one quick note, Spark 4.2 is built by the whole Spark community. More than 260 contributors from the community. So everything we show is open source. Spark 4.2, in one line, more semantics, AI, Python, CDC, and operations powers, all in the same engine. So the number, over 1,600 Jiras, and from over 260 contributors. So one goal ties it together, make analytics and AI more native to Spark. So we build a talk around the 5 benefits. 1, define choose once, matches view. 2, reach Spark from everywhere. Connect, PySpark, Arrow, Python data source. 3, AI native analytics in SQL. Vectors, sketches, geospatial. 4, move changing data safely. Auto CDC changes DSV2 streaming. 5, operator and evolve predictably. The UI, the better UI, reliability, faster release. And looking ahead, we started the project Feather to make the small data faster. And the other ongoing speed will be presented too. So I covered the first 3, and the DB will cover the rest. So this is the whole release on one slide. 6 groups, about 24 features. We will not cover them all. Just see how much is here. Keep it as a map. Let's start. Benefit 1. Define choose once. Let's start with the problem. So today's takeaway is move your top dashboard metrics into a metrics view. So the problem, in plain words, revenue per user is a ratio. Ratio cannot be summed directly. You cannot average them across the groups and get the right answer. So when every team writes a formula by hand, so the dashboard drift apart. Same metrics, different numbers. Let me show how it breaks. Here it is in one table, 2 countries. Revenue and active users adds up fine, but revenue per user is a ratio. So if you average the 2 rows, you get a 15. That is wrong. So the right answer is the total revenue over the total users. So that is 13.33. So where should this metrics live? So it is right every time. So that is a semantics layer problem. Every company already has a semantic layer, but it is scattered. Revenue, active users, and the churn are defined again and again in BI tools, in DBT, in notebooks. The cost is real. The dashboard disagree. No one owns the definition, and it is about correctness. So ratios and the count distinct break when you roll up. Client tools sit outside the engine, so they cannot enforce it. AI needs this too. An agent must answer the same way every time. A governed metrics view gives the BI and the AI one source of truth. So 4.2 adds metrics view. That is a SPIP, Spark 54119. You define the matrix once, then you query it by any breakdown. So there are two parts. Dimensions are the way to slice. Measures a new column type that aggregate without a fixed group by. So this stop drift. Ratio and the distinct counts stay correct for every grouping. And the measures can build on other measures. It lives in the engine and the catalog. So the optimizer keeps it correct, and the permissions are the same everywhere. One source of truth for SQL, BI, and AI. So 3 ideas, not syntax. A dimension is how people slice a matrix. A measure is what business cares about. Here it is revenue per user, a ratio. The query asks by any breakdown. The point is not syntax. The matrix is now an object Spark understand. So it is correct every time for everyone now. So please try it. So in 4.2, this is the latest big features. Now, how to connect Spark. So we can reach Spark from everywhere. First, Spark Connect. So take away, call from your own service language. So the idea is simple. Your client builds a plan. It opens a gRPC stream. The server resolves the plan, optimize it, run it, and then send the error batch back. The client is seen. It does not need a full Spark runtime and no JVM next to your app. So the client and the cluster can change on their own. You can upgrade your server easily without affecting your client. Before connect, using Spark from another runtime means wrapping it or embedding it. With connect, Spark is a service API. Your app does not need to be a Spark app. The point is a use case, not a language list. So the Rust service submit work. A Python notebook connects to a remote server or remote cluster. A small app uses Spark without packaging it. Python and Scala shipped with Spark. And Go, Swift, Rust, Scala 3, R, TypeScript, .NET speak the same protocol. So the next step is to make your UDF portable. So the DB will come back to that in the looking ahead section. In 4.2, we keep closing the gap with a classic driver. Old RDD helpers comes to connect. Zip with index to JSON, empty data frame, and the read.json, CSV, XML can take a data frame. So there's a new data status API, and the errors are cleaner. For example, when you use a column from the wrong data frame, and the client fires names and the line number. So debugging becomes easier. PySpark in Spark 4.2 is moving to error-first pass. Existing Python UDF get faster by default. Hot paths can use a native arrow UDF, and the Python teams can just get a first-class data source, plus better profiling and debugging. So today's takeaway is simple. Upgrade for the free speed up. Then optimize only the Python code that matters. So important part is the default. In 4.1, you already turn it on. But in 4.2, you don't need to do anything. So arrow Python UDF are the default. The old UDF, your old Python UDF just run faster. Arrow IPC between the JVM and the Python is on. And the arrow input skip one conversion step. The upgrade story this speed with no code change. The same UDF you always write, no new decorator, no rewrite, but the engine moves the ideas as arrow. Same code, faster. 4.2 continue the arrow first direction. The decorator arrow UDF since 4.1, a parallel array in, a parallel array out. It removes the pandas round trip, one less conversion. So in our benchmark, it is about 10% faster and 40% less memory than a regular pandas UDF. The big win is a type fidelity. So pandas mangles types, and the nested types are awkward. So arrow keeps the nested and the structured type, and use a Python standard correction and stays synced friends even on the nested data. So at a different level, you also get map in arrow, apply in arrow, and to arrow. So the arrow UDF decorators, arrays in, arrays out, no two pandas, no round trip, column from start to end. Build Spark readers and writer fully in Python, batch or streaming, no JVM, no Scala, register once, use spark.read.format. Tap a growing ecosystem of connectors. You can use ARM to draft long tail sources. So this is ecosystem today. Connectors, the community already built in pure Python. Before you learn the JVM API, now you just write Python. This is a full customized source. A reader class, register it, read it like any format. That's the whole thing. New in 4.2, you can profile this patented source like UDF for times, memory, one config, turn it on. Then you can see where your time, memory go in your read and write code. Your connector is no longer a black box. One interops worth calling out is a pipe capture protocol. Spark now speaks the arrow C data interface. So you hand data to Porous, DB, or other arrow native tools with no copy. So when both sides supported, less glue, less overhead between the Spark and the rest of your Python stack. A Sparked frame goes straight to the Porous or DB, so the arrow C data interface. So when both sides supported, they share the same arrow memory, no copy, no serialization. Now debugging. Your Python UDF runs in a Python worker on an executor, far from your notebook, when it hangs before you saw nothing. In 4.2, you can see the hang. The worker dump is statues, and idle workers are dumped and killed. Now, one provider covers Python, pandas, and arrow UDF, CPU and memory by lines. It works on Spark Connect too. And you can use a Python login interface inside a UDF. Then read the logs back as a table. So the start worker with the statues shown for you and the UDF log, you can read back as a normal table. This is just an example. And AI native analytics in SQL. Today, these workloads are scattered. A vector system here, verbals, SQL there, 4.2 brings them into the engine. vector functions, nearest by, qualify, sketches, geospatial. Embeddings are now normal table data. The first need is simple. Compare two vectors where the data lives. Spark 4.2 adds a vector function for that. Cosine similarity, inner products, L2 distance, normalize, and aggregations, all in SQL. So this is scoring primitive, not an index yet. The simplest vector search, one query vector against a table, score, sort, take the top 10. It is just SQL. But the real workloads have many query rows, act top products for every user. By hand, that means a cross-join, a window, and a filter. So nearest by, the latest feature, replaces that. Now we generalize from one query vector to many query rows. For each left row, find the k-best right rows. The score is usually similarity, but it can be any expression. The old way, cross-join, row number, filter, hides the intent. Nearest by makes it explicit. In 4.2, exact is a brute force top K, just with a clearer SQL. Approx keeps the same shape ready for the future index-backed plans. The same search, now batch. For each user, the top 10 products by similarity. The point is the shape, not the function. No cross-join, no windows, no filter. Vector search is a common case, but the nearest by fits any top K row, top K joins. So this demos are exact. Process keeps the query stable, but for smarter execution later. Before and now, 4 times. Each one removes a pattern we have written for years. Qualify, top N without subquery. Filter, conditional aggregate now runs over a window too. Some filter were over that was rejected before 4.2. Pivot with alias, readable columns, and the cursor, row-by-row logics in pure SQL script. So the takeaway is reach for the qualify first and use filter over window where you use a subquery. Set path is a SQL search path. Before, every name needs the full catalog and the schema. Now you set the path once. The unqualified names resolved across the schemas. It is saved in the views. So resolution stays reproducible, but it is opt-in. You need to turn on this config. It is not import. Basically, objects stay where they are. You just improve the analyzer. A few more compatibility wins, like the time data type, timestamp with local time zone. By the way, time data type is not on by default. It's a preview. So it's highly possible 4.3, we can create the time data type. And more built-in functions. Sketches are small. Probabilistic summaries, one pass, small memory, bounded errors. Spark already posed them as a SQL aggregate before. Now in the 4.2, we introduce a tuple sketches. So this is tuple sketches. Distinct user a revenue summary in one pass. Then we can merge daily sketches into a month instead with no rescan. So location data is everywhere. Delivery, IoT, map, risk. 4.2 add geometry and geography as a native SQL type. On by default, no actual package. Geometry is a flag, geography is a globe, so there's a full SRID support. You read and write in packet. and the type as SRD are kept. It works in SQL-defined PySpark, and it follows open Parquet and Esper geospatial spec. It works across the engine. So Spark 4.2 support the multiple ST functions, and the SRID helps build a geometry, write it into Parquet, and read it back. The type and SRID tips. So far, 4.2 brings more logics into engine, matches, Python, SQL, but analytics is not only query. The data changes underneath you. So DB will show the 4.2, how Spark 4.2 changes itself. Safer, CDC, streaming, DSV2. DB.
For the first portion. Is my mic on? Okay, cool. Yeah, so I'm gonna take over and talk about some of the new feature in Spark 4.2. So the first one is auto CDC and SDP. So I think it's a hard problem actually. How do we keep a table in sync with a stream of the changes? So okay, let's say a common use case. Let's say we have layout table and we want to have it in sync with some of the operational change fee. So let's say we have a customer, we have a version 1 with customer 101, say that is in SF. And then you have another data coming in version 3, say Seattle. Then you have version 2, there is arrival late, and it says Los Angeles, right? So if you want to process by arrival order, LA can, override Seattle, but it's not what we want actually, even though LA is the order. So, and let's say we have version 4, we want to delete the data. Right, so a CDC event has a 4 part. So one is a key that is by the ID over here, customer ID, operation. You have different operation and sequence, and also the data payload. So now the key is the raw identity, and the sequence is a business order. So if you want to process this kind of data, you can handwritten for each batch, a lot of merge stuff. And it's gonna turn a really simple problem into a huge challenging, disputed computational problem. You need to handle the ordering, detube, retry. So a lot of time you can cause a lot of mistake. So in SDP, we have a new feature inside Spark 4.2 we call auto CDC, change of data capture. This can help to address this issue. So SDP here, Spark Declarative Pipeline, is a pipeline manager. It's run as a pipeline. It's handle the dependency, data dependency, streaming, checkpoint for you automatically. And it's a special flow. Auto CDC is one of the special flow inside SDP. And you give a key, customer ID, a sequential column version, and they handle it for you. So there are 2 types of the auto CDC. One is SCD type 1, and one is SCD type 2. SCD type 1 only keep the latest result. So as you see from the first example over here, the last one we will delete the data on the customer 101. So we only keep the record of 102. So SCD type 1 actually, 1 second. Only keep the final result. And we are working on open sourcing the type 2 to open source community. The PI is ready actually, but we haven't been able to merge it into Spark 4.2 in time. So this will be part of Spark 4.3. So we will be able to keep the entire history of the CDC. Okay, and on the structured streaming side, we also add a bunch of new features actually. So there will be a full talk by Anish and Jerry on this Thursday. And if you are interested in, please attend the talk. And here will be the brief overview on the streaming side. So Spark 4.2, we have some optimization on stream-to-stream join, optimization with fast watermark eviction, state store integrity check with low-level checksum, and also the new PySpark support for real-time streaming mode. So for the stream-to-stream join, in Spark 4.1, we add a virtual column family that move the join state into one RockDB store instead of 4. That give a good performance scan. But still, watermark eviction can still scan too much data in join state. And in Spark 4.2, the state data source can read the join state directly and from the state format v4. And this add a secondary index watermark eviction. And this also help to optimize the left semi and non-outer join performance scan. So over here, we see that the eviction scan go from about 2 seconds for a full scan to about like 30 milliseconds bounded per million row. So it's a huge performance scan in Spark 4.2. And also for the state store integrity, in 4.1, we add a state machine locking. So RocksDB has a single owner plus file level integrity checksum, but the manual recovery paths are still too common and it's really costly. So 4.2, we go fine-grain a low-level checksum using CRC32 sampling. And we also have the new feature like automatic snapshot repair, robust checkpoint v2, and also the RocksDB memory usage will be unified within the unified memory manager within Spark. So this helps to manage the RocksDB memory consumption as well. And next is data source v2. So data source v2 is a way how we can connect Spark to data. And this will be a short summary of what Sihan and Anton gonna talk about later this week. So it's a standard API DSB2 for data source. Previously, it was mostly used in Iceberg, but now Delta is transitioned to use DSB2 as well as part of the unification between Delta and Iceberg. And connector, this provides a way that we have a consistent way to handle metadata, small, and also have a contract between Spark and data. So I'm gonna talk about more. And with that, Spark can do heavy lifting between analysis, planning, optimization, and finally execution. So those don't have to be implemented inside the data source. And this gives user more consistent syntax and behavior between different data sources. So we have a lot of momentum recently in V1, V2, in DSB2 between Spark 4.1 and 4.2 as part of the unification. We try to bring Delta and Iceberg closer. We have some improvement on DML hardening, how we handle schema evolution inside Spark. Right summary is a DML matrix, how to handle transaction, change log, and also partition predicate. I'm gonna share about more. So for first class CDC, so there will be a short version of Gen Liang and Johan CDC implementation talk on Thursday. So we were talking about CDC is on the consumer side that we can use CDC inside SDP, but here is how we actually implement CDC inside inside the data source. So previously, before this, as part of DSV2 framework, Delta, Iceberg, and Hoodie, they also support change fee. But each has its own API and also different implementation and different default behavior. And now in Spark 4.2, we make it as a first-class citizen so that we have a single change syntax, one algorithm inside Spark to support CDC. So the first user-facing changes is one surface, right? So today, each connector has its own CDC implementation, has different API and syntax. Now we unified it into a single SQL keyword as a changes inside Spark 4.2. And this can, help to ask the difference between different version, different timestamp, or stream changes between different table, from a table. So so on the connector side, the implementation is pretty tiny and intentionally, and it's only declared the output column, provide a scan builder for low changes low, and the name of the low identity and low version columns, and then the rest can be handled by Spark. Okay, 1 second. Okay, the next is schema evolution. So it's another area that Spark DSV2 has been go up in the past 1 year. So a schema evolution is how Spark can compare the source and target. They can include in a nested column, it's compare where need to be changes, right? Whether you want to add a new column or widen the type, upcasting from low integer to long, fill in the missing target field with null or default. And the basic concept is that the connector can decide whether it's valid for this table format or not, but Spark can have a suggestion on this one, have some implementation. So Delta and Iceberg, they might not have this widening rule, but DSV2 give each connector a place where they can reject it or accept it. So we can have a more unified behavior if the data source feel like it makes sense for a specific data source. So so a new column, let's say, appear in the source with schema evolution. Spark can compute the schema changes and ask connector whether this apply is valid or not. So this is the whole concept of schema evolution here. And the next area we have been improving is transaction. So DML is basically doing read, transform, and write back. So without isolation, a writer can override the changes in neighbor source. So in Spark 4.2, we add a transaction API that Spark can have a transaction for DML. So the connector can stage change, track reading, validate a commit time, so that avoid transactional issue. So now we only support single DML statement, and multi-statement and cross-catalog transaction would be our future work. And another area is on the metrics side. So on the DML, we add a merge operation metrics in Spark 4.1. And in Spark 4.2, we are adding update and delete metrics. And Spark can collect the metrics in the background and then commit it through the DSV2 commit API. Okay, and finally, on the DSV2 area, we work on the partition predicate. So it's a really big gap for DSV2 right now. So in DSV1, because we expose the catalyst expression directly to data source, so they can do a lot of optimization. For example, they can push down a UDF equal to certain stuff, and they can be pushed down. However, in a DSV2 framework, it's not allowed because we only expose a smaller set of the expression that can be allowed to use in DSV2 framework. So UDF and non-standard expression cannot be used in the predicate. So we add a new interface, partition predicate, that can bring specific catalyst predicate into DSV2 framework to provide better performance. Less data will be read and faster query. Okay, next, we also have some performance UI improvement. So the web UI, we have new look, a dark mode, faster interface, and interactive SQL planning, and also some packet optimization on the vectorized packetry, pre-aggregation, and also some cogent improvement. And we also improve like an I/O part, so we use arrow to transfer data between JVM and Python, as Xiao has mentioned. This causes less memory overhead without any code changes. And also, we support Spark, in Spark 4.2, we start to support JVM 25. And in Kubernetes area, we also support many new features like, Impress executor, PVC resizing, having smaller image, and some of the network policy isolation. And we also improve history server as well. That is quite a bit of the improvement. Okay. Okay, and then looking for the future. So in Spark 4.3, we plan to work on many areas. The first one is project failure. So Spark is, one second. Yeah, so Spark is really good in large scale, reading petabyte of data, doing a huge job. However, in the laptop experience, it may not be necessarily the best environment because it was designed as a distributed compute engine, so a lot of overhead. For example, like a shuffle, the planning is for distributed. So we create a new project called Project Fader that Daniel will talk about that later today. And it's targeted for small job, for query less than 100 megabytes. That can still take seconds, but we want to reduce it to millisecond. And how we can do it? So we are able to do it by having a faster planning and scheduling for local mode, single pass analyzer, for optimization on the single file query that can make it as a single task so that we don't have shuffle directly. We also have the arrow native caching. So the cache will be cached in the native memory with the arrow format, and that can be used by UDF as well. So UDF can now take arrow as an input without any data conversion. And also we have a shuffle-free local execution as well. They can eliminate writing data to local disk even though it's a single laptop mode. So I think the goal here is not like, it's different like a DuckDB or Polars. So the value here is that user can start small, doing local development with first efficiency, and they can scale up to large scale in production. So I think that's the key difference between other single node engine. And another area we are working on is a language-agnostic UDF protocol. So right now we are support different language for the Spark Connect. But for the UDF part, we are not able to support different language, mostly Scala and Python. So we are building a new framework where you can execute the UDF using different language, and even it can be run on the remote server. So you can decouple the Spark cluster and UDF runner. So Haiyang and Tian will talk about more detail this Thursday on this. Okay. And this SPIP has been passed, so we have been landing new code into open source Spark right now, so feel free to take the preview. And we are also supporting the nanosecond precision timestamp. It's a SPIP has been passed, and we have been actively working on this on the open source community. Okay, and there are other improvements on the Spark 4.3, streaming and pipeline SDP improvement. For example, like a SCD type 2 would be supported in Spark 4.3. Okay, and I think it's really important that we can release the Spark faster. We have been doing it like twice a year release schedule, and we have been doing a lot of innovation in open source Spark, but it takes some time to lend it to the people who are actually can use it in production. So, in the community, we decided that we want to do a 2-layer model. So we have a quarterly minor release that we can release new feature, and we are able to roll out feature much more quicker, but without any dependency changes. And every year, we will launch a new mature version where we can do breaking changes, so we can accelerate the development velocity in open source Spark community. Yeah, so all of them are the new stuff in the Spark 4.3, Spark 4.2, and then the future work for Spark 4.3. So yeah, thank you for the talk, and any question is welcome.